You have 100 kilograms of potatoes. Now, these potatoes are 99% water. You let them dry until they are 98% water. How much do the potatoes weigh now? You might think that the weight barely changes, but in reality, the answer is 50 kilograms. Today, we're diving into a few counterintuitive paradoxes, from the simple logic behind the potato paradox to the calculus used to solve the ant on a rope problem. Let's get back to the potato paradox. At first, there was 99% water and 1% solid, so 1 kilogram of solid potato and 99 kilograms of water, and that 1 kilogram doesn't change. After drying, they are now 98% water, so 2% solid. That 1 kilogram of solid is now 2% of the total weight, so the total weight is 50 kilograms. Next up is the Monty Hall problem. Here's the problem. You're on a game show. There are 3 doors. Behind one is a car, and you get to keep it if you choose the right door. You choose a door, say door A. The host opens door B, revealing that there's nothing behind it. The host then asks you if you would like to switch to door C. You would think that there's a 50% chance of winning whether you switch or not. Or maybe the host wants to save the show some money. But actually, the odds of winning doubles if you switch. At first, each door had a 1/3 chance of having the car behind it. That means there's a 1/3 chance of the car being behind door A and a 2/3 chance of the car being behind door B and C combined. When the host opens door B that has nothing behind it, that combined 2/3 goes to door C, so your chance of winning doubles. We can also use a chart to solve this problem by listing out every scenario. How many people are needed for there to be a 50% chance that 2 of them share the same birthday? Take a guess. 183? 150? Actually, the answer is 23. To solve this problem, it's easier to compute the chance that no 2 people share a birthday. The first person can have any birthday, so 365 possible birthdays. The second person has to avoid sharing the same birthday with the first person, so 364 out of 365 possible birthdays. The third person has 363, and so on. The nth person has 365 minus n plus 1 possible birthdays. Multiply all these fractions, and we get the chance of no 2 people sharing a birthday when there are n people. When n equals 23, that chance is about 49%. So the probability that 2 people share a birthday is 1 minus that number, which is more than 50%. In a room of 75, that number increases to 99.9%. Now let's take a look at the ant on a rope paradox. This is a 1 meter long rope. It stretches 1 meter per second. On this rope at the left end is a 1 centimeter long ant. It crawls 1 centimeter per second. Will it be able to reach the right end of the rope? At first, it seems impossible, but in fact, the ant will eventually reach the right end because every part of the rope, including the bit under the ant, stretches forward. Let's do the math. The initial rope length, L of 0, is 1 meter or 100 centimeters. At second t, the rope's length L of t is t plus 1 meters or 100 times t plus 1 centimeters. We track the ant's position as fraction of the total rope length. In tiny time delta t, the ant crawls 1 times delta t centimeters, so it gains the fraction delta t over L of t, or delta t over 100 times t plus 1 of the total rope. Sum up all the fractions gained in every tiny time interval, and we get this. The total fraction the ant needs is 1, the whole rope. Using the logarithmic integral rule, we find that the integral is 1 over 100 times the natural logarithm of t plus 1. We solve for when the integral equals 1, or when the ant crawls the length of the whole rope. We find that t equals e to the power of 100 minus 1 seconds. That's approximately this many seconds, or 850 decillion years. That's a long time, but it's not infinite, and the ant does reach the end.